Hey class, today I will be teaching you about deterministic finite automata, also known as DFAs for short, and why you should care about them. But first, I want to ask you a question. What comes to mind when you think of a computer? If we look on the Wikipedia page for computer, here's what comes up at the time of recording this video. A vacuum tube computer, a mainframe computer, a desktop computer, a supercomputer, a video game console, and a smartphone. We also have a human computer because, believe it or not, a computer used to be a job for people. But what about this? Could this be a computer? In this video, I hope I can convince you that yes, this little thing called the DFA is a computer, and even though it's simple, it can do a lot. But first things first, what is a DFA? In one sentence, a DFA is a collection of states and transitions that consumes input, character by character, and transitions between states accordingly. We have a start state, denoted by the circle with a triangle attached to it. A DFA usually has one or more accepting states, also called final states, though it can also have zero. An accepting state is denoted by two circles instead of one. After we consume the entire input, if we end up in an accepting state, we say that our input is accepted by the DFA. We call the set of inputs accepted by the DFA the language of the DFA. There are two more important properties of a DFA. We call that DFA stands for Deterministic Finite Automaton. This means that each state must have transitions out for each input character. For example, you can see that in our DFA on the left, each state has an outgoing arrow for both 0 and 1. This also means that DFAs have a finite number of states and transitions. We just saw a picture representation of a DFA, but there is also a commonly used 5-tuple representation. The 5-tuple contains Q, sigma, delta, Q0, and F, where Q is the set of finite states, sigma is the alphabet, which is the finite set of allowable input symbols. Delta is the function that defines transitions between states based on the current state and the current symbol. Q0 is the start state, and F is the set of accepting states. If that seems like a lot, don't worry, because we're about to go over an example. Here's our DFA from earlier, and now we are going to convert it into a 5-tuple. We can see we have three states, Q0, Q1, and Q2, so that becomes our big Q. It looks like we only have the characters 0 or 1 in our input, so that becomes our alphabet, sigma. For delta, what I've done is for each state in transition in our picture, I create a rule where our delta function takes in the state and transition symbol and outputs the next state. That looks something like this. Then, we can see that Q0 is our start state because there is a triangle attached to it. Lastly, Q0 is also our only accept state because it's the only state with two circles. So, we've just converted this picture representation of a DFA into a 5-tuple. Now, let's go over an example of how to construct a DFA. For this example, we are going to create a DFA whose language is bit strings that end with 100. A bit string is just a string that only contains zeros and ones, which means that our alphabet is limited to just 0 and 1. Now, I will walk you through my thought process of how I would construct this. First, I need a start state. It's not really intuitive to me to call my states things like Q0, Q1, etc., so I try to keep track of what the states mean. For Q0, we're just going to call this a default state, because nothing interesting is happening yet. Then, if I see a 0, I want to go back into this default state, because we haven't seen a 1 recently, so really there's nothing interesting going on. If I see a 1, however, I want to keep track of that, so I will move to a new state Q1, which I will call ends in 1. Now I want to be clear. This does not mean that the entire string ends in 1. Since the input is consumed character by character, all this means is that the consumed input up to the current character ends in 1. Now, if I see another 1, our consumed input still ends in 1, so I will go back to the same state. If I see a 0, on the other hand, I want to keep track of that, so I will move to a new state, Q2, which I will call ends in 10. Now if I see a 1, our consumed input now ends in 1, which means I go back to Q1. If it ends in 0, our consumed input now ends in 100, so I want to transition to a new state, Q3. This is what I'm looking for, so I will make Q3 an accepting state. If I'm in Q3 and I see a 1, now our input no longer ends in 100, but it does end in 1, which means I move back to Q1. If I'm in Q3 and I see a 0, that means I haven't seen a 1 in my last 3 digits, which means I go back to the default state. Now, our DFA is complete. But how do we know if it actually works? Whenever we are tasked with creating a DFA, it's a good idea to generate a list of test strings, that is, strings that we expect our DFA to accept and strings that we expect our DFA to reject. One thing I like to do is that I always include the empty string because that's an edge case that's easy to miss. Now, let's run our DFA on the first input, 1, 0, 0. First, we start in the start state, Q0. Then we see a 1, so we go to Q1. Our next character is 0, which means we go to Q2. Our next character is 0 again, which means we go to Q3. Now we have no more input left to consume. We end up in an accepting state, so we accept the input of 1, 0, 0, which is what we expected. Now that you understand how to test a DFA on an input string, I'm going to run the rest of the animations without narration. I'm going to take a quick pause here to show you what happens in the case of the empty string. We start off in the start state, Q0, and since we have no input, we also end there. Since Q0 is not an accepting state, we reject the empty string. Now, back to the animation. So, we have shown that our DFA successfully works on all of our test strings. One thing that I would like to point out is that while I came up with the DFA pretty quickly in this video, in reality, usually it takes a lot of trial and error to get a correct DFA. You will most likely have to go back and forth a lot between drawing and testing your DFA. So, don't get discouraged if your DFA does not work on the first try. This is a normal part of building DFAs, and also, you'll find that the more DFAs you create, the better your intuition becomes. With that being said, now it's your turn. Can you create a DFA whose language is bit strings where the first and last character are the same? I encourage you to pause the video to try this out for yourself. Here is my sample answer. I'm not going to go over this in detail, but I want to point out a few observations. First, notice that we can have more than one accept state. My DFA has 3. You might also notice that the top half and the bottom half are nearly identical, they just have the zeros and ones switched. If you encounter a problem like this one where you don't have to deal with the exact characters of the input, one strategy might be to create branching paths like I did here. The last thing I want to point out is don't forget the empty string. It's easy to miss, but the empty string has no characters, so it's vacuously true that the first and last characters are the same, which means it should be accepted. Always remember the empty string, and remember that your start state can be an accepting state too. Here is the 5-tuple representation of my solution and some test strings I came up with. Feel free to pause the video if you need some more time to look at this. So, why should you care about DFAs? First of all, DFAs are a great introduction to theory of computation. This is a rich field which deals with questions like, can we compute this? And what tools would I need to compute this? If this video on DFAs was interesting to you, I recommend that you check out some more theory of computation. You might even be interested in my earlier video about lambda calculus. Why else should you care about DFAs? I personally think DFAs are really cool because they're simple but still effective. Take a look at these examples where DFAs could be used. Have you ever tried to create an online account, but when you try to type in your password, all of a sudden the website's like, must contain a capital letter, must contain a special character, must be between 8 and 16 characters. Turns out, DFAs are really good at pattern matching, so your password could be validated by a DFA. Have you ever tried to search for text on a page? Detecting whether or not a given word is on a page can also be computed by a DFA. And you've probably never done this before, but a DFA can also be used to verify the presence of a DNA subsequence in a larger DNA strand. Plot twist! Sometimes we don't care about DFAs, and I'm going to tell you when. We don't care about DFAs when we want to do any of the following: count, arithmetic, parse nested structures such as parentheses, have infinite memory because remember, the F in DFA stands for finite. Then, if DFAs aren't powerful enough, how do we do these things? If you're really dying to know, then you should really check out theory of computation as well as my lambda calculus video. Otherwise, stay tuned because I'll cover it eventually. Let's summarize what we've learned today. We learned that a DFA is a collection of states and transitions that consumes input, character by character, and transitions between states accordingly. A DFA usually has one or more accepting states, also known as final states, and when we end an accepting state after consuming an entire input, we say that input is accepted by the DFA. The set of accepted inputs is called the language of the DFA. DFA stands for Deterministic Finite Automaton, deterministic meaning that each state must have transitions out for each character in the alphabet, and finite meaning there are a finite number of states and transitions. We learned about the 5-tuple representation, which consists of the set of states, alphabet, transition function, start state, and set of accepting states. Lastly, we learned that we should care about DFAs because they are a good introduction to theory of computation. They are simple, but they can do a lot, like check passwords and look for DNA subsequences. But we also learned that sometimes we don't care about DFAs because they're not powerful enough to do everything we want, like counting or arithmetic. Thank you so much for watching, and please, feel free to comment any topics you would like me to cover next, or any feedback for how I can improve my videos. As always, this is your CS Professor of Fun.